Okie dokie, chokies. Hope you had a good long weekend. I'm going to continue on with review of Lhopitals Rule, improper integrals, and partial fractions. And I put some homework up on WebAssign so you could get practice. I'm a little bit trying to stay away from the AP practice, although I will open it up. I mean, the AP classroom. Although I will open up problems. And the reason is because you have to upload work. Some of you are having trouble uploading the work. And it's just more work and more of a pain than what we need to endure. So I think what I'm going to do is I'm just going to find random FRQs and post them to EDSB, and you can do the work there and then just ask me any questions. And I think what I'll do is I'll make little videos of the solutions to those problems. Also, some of you asked me for a video on the solutions to the last AP classroom where I put some series up there. So I'll be making that later on this morning and posting it for you to view. Okay, so let's get started with this. Lhopitals Rule. So remember, you can only use Lhopitals Rule when you have the indeterminate form 0 over 0 or infinity over infinity. And also remember that there are other indeterminate forms that could happen. This one here being the most common that you might encounter. This one too is pretty common. So these two I would be on the lookout for on an AP exam. But you cannot use Lhopitals Rule if you have these two forms. So you have to get it into 0 over 0, infinity over infinity, okay, before you can use the rule. All right, so let's just do a couple simple examples. For example, you want to show that the limit as x approaches 0 of 1 minus cos x over x is equal to 0. And you know that if you go ahead and plug the 0 in right away, you're going to have 1 minus the cosine of 0. The cosine of 0 is 1. So you have 1 minus 1, which is 0 over 0. So immediately you have that 0 over 0 form. And so that's your red flag that you need to use the rule of L'Hopital. So what we do is we take the derivative of the top, the numerator, and then the derivative of the denominator. And then we try plugging the number in again and see what happens. In this case here, we get the sign of 0, which is 0. And when we plug we can't plug, but the derivative of x is 1, so the limit as x approaches 0 of a number is the number itself. So we get 0 over 1, which is 0. Okay. In this case here, another example, we have this cubic, and again, if I just plug the 1 in, and I did that to show you, we get this 0 over 0 situation. That tells us we need to use L'Hopital's rule. Well, we take the derivative of the numerator, derivative of the denominator, and we plug the 1 in again. And when we do, we still get 0 over 0. So this is called the repeated use of L'Hopital's rule. So we take the derivative top and bottom yet again, and we plug the number in, and what we end up with is a 6. Okay, so just keep taking the derivative of the top and the bottom until you get a number or something weird like infinity. Here's one with infinity. Okay, so here's the other case, infinity over infinity. That means it's perfectly fine to use L'Hopital's rule. So if I plug infinity in, I'm going to get infinity over infinity. So I took the derivative of the top, took the derivative of the bottom, plugged infinity in, and still got infinity over infinity. So that means I have to do it again. When I take the derivative of the numerator, I get a 4. Derivative of denominator, I get a 6, which is 2/3, and the limit of a number is the number itself. And so we get 2/3. Here's one of those situations where you might think, you have to use, and by the way, this is a minus, it didn't come out that good, where you might have to use, say, I can't think of the word this morning. I'll think of it and get back to you. Anyway, if you plug infinity in, you're going to get infinity times 0, which is not 0 over 0 or infinity over infinity. So that means you're going to have to play around with this. You're going to have to rework this to get it into the form of 0 over 0 or infinity over divided by infinity. So we know that e to the minus x is 1 over e to the x. So I'm just rewriting this. And at this point, if I plug infinity in, then I get that indeterminate form for which I know I can use Lhopitals Rule. So I went ahead and took derivative of the numerator and denominator, plugged infinity in, got the same thing again, took the derivative yet again of the numerator and the denominator, and got 2 over infinity, which is 0. Okay, still not too bad. I'm still trying to think of the term. Integration by parts. That's what I was thinking. Integration by part. So this is not a by part. Not that you couldn't get one. You most certainly could, because that's a BC topic. But it's not that at all. Generally, you're going to have to rewrite these. So a lot of kids think of integration by parts when they see something that looks like it's a difficult type of a problem. So don't think that. Okay, this one here, I should have put 2 stars, so I'll do that now. The form 1 to infinity, this is fair game. This is not hard, but it is fair game, and you have to be on the lookout for it. And this is going to be something where you get 1 to the infinity. So the problem is given like this, and if I plug my infinity in right away, I get 1 plus 0, which is 1 to the infinite power. So I get this situation right here. And again, I can't use Lhopitals Rule with that. So I'm going to have to do something here to fix this, so that way I can get an indeterminate form that I can use Lhopitals Rule with. So it's a little bit of work. Like I said, it's not hard. You just have to be on the lookout for it, especially when you see 1 to the infinity. That's when you know you're going to have to do the following. Number 1, you're going to assume that the limit exists, okay? And what you're going to do is you're going to say, you're just going to write y equals whatever's given, okay? So the only difference between this and this is I have y equals that limit. And then you have to take the natural log of both sides. So I took the natural log of both sides. And I want you to know that, logarithms are continuous. And so all you have to do is, swap these two. So that's what I'm doing here. I'm working just on the right-hand side. Do not forget about your left-hand side. But I'm taking this here, and you notice that I put the logarithm inside, the natural log inside. So I went from this to swapping them, all right? And then by rules of exponents, I can bring this exponent down in the front, so I did that here, okay? And at this point, I went ahead and plugged in infinity, and what I get is infinity times the natural log of 1 plus 0 is ln 1 is 0. So I get infinity times 0. So I no longer have this 1 to the infinite power situation, which was up here. I have infinity times 0. So that means I'm getting closer. All right. So I'm going to keep working this right-hand side. And I'm going to do a little trick. I'm going to divide up and down by 1 over x. Okay. So remember, this is all over 1. So if I multiply 1 over x times x, I get a 1 there. And then if I multiply the denominator by 1 over x, I get 1 over x. And now when I plug infinity in, I get that 0 over 0 situation that I want. And at this point, I'm going to have to use a little bit of algebra. All right. So what I have to do here is I have to take the derivative of the numerator, right? Because I can use L'Hopital. So I'm going to take the derivative of the numerator, which is this is a composite. So the derivative of the outer is 1 over x, but x we have to replace the function inside, times derivative of the inner function. So the derivative of 1 plus 1 over x is negative 1 over x squared, all over derivative of the bottom, which is negative 1 over x squared. And those cancel. All right, so that's what I mean when I say a little bit of algebra. And at this point here, what we're left with is the limit. So let me move this over. The limit of just this piece here, because those two are going to cancel out. Right? And if I plug infinity in, I'm going to have 1 plus 1 over 1 plus 1 over infinity, or 1 over 1 plus 0, which is 1. So it's 1. Now this is just the right-hand side. I said you can't forget about the left-hand side. So what you have is ln y is equal to 1. Then you're going to have to exponentiate both sides, and you know that e to the natural log, they're inverse of each other, so they're going to go away. So what you're left with is y is equal to e. So be careful with that. I think I found one on WebAssign that I included, but if not, let me know, and I can give you some more examples of something like this. Very important. Moving on to 10.2. So this is from the best book, chapter 10, improper integrals. Okay, so an integral is going to be improper if the lower or upper limit of integration is infinity. All right. In other words, these are not finite, these are infinite. And so what we have to do is we have to take the form, this improper form, and we have to write it in a proper form. And how we do that is I use T, you can use B, you can use, because you're used to A to B, you can use whatever letter you want. But you take the limit, so you call the unbounded, this is the upper bound, which is infinite here. You take this infinite upper bound and you take the limit as T approaches that upper bound. And you replace the infinity on the upper bound in the integral with that letter, which in my case is T. Okay, so I'm just going to rewrite this like this. Likewise, if the lower bound is infinity or infinite, then what we do is we take the limit as T approaches negative infinity, and we replace the lower bound negative infinity with that T to B of the function. All right, if the limit exists, the improper interval is going to converge, and if it does not exist, then the improper interval is going to diverge. So that's technically what you're going to be looking for, is does it converge or does it diverge? So a very simple example, here I've got an upper bound that's infinite of 1 over x dx. So I'm rewriting this, I'm going to replace this with a t, so I'm going to see the limit as t approaches that infinity of the integral 1 to t 1 over x dx. And the idea is I'm going to integrate this and simplify it, and then I'm going to take the limit of it, right? So the limit kind of comes last. So if we integrate this, we get the natural log absolute value of x, and we have to evaluate that from 1 to t, which is going to give us ln t minus ln 1. Don't forget ln 1 is 0. So what we really have here then is the limit as t approaches infinity of the natural log of t, and when I plug infinity in there, I get infinity. So what I say is, because I don't get a number, okay, I get infinity, I say that the improper integral diverges, or that the original integral diverges. Here's another one. And you know this, right? You know this function from series now. Here's another one. And I'm pretty sure I actually did these two in class. But here we've got 1 over x squared dx, so just a minor little change. However, a big difference in divergence or convergence. And again, we're going to do the same thing, right? We're going to replace that upper bound, that infinite bound, with t. We're going to take the limit of that integral. So I'm writing this as x to the minus 2, so I can integrate it easily. And what we get when we integrate is negative 1 over x. We have to evaluate that from 1 to t. So again, I've got my limit symbol there. If I plug in the t, I get negative 1 over t minus a negative 1 over 1. So we've got the limit of negative 1 over t plus 1. If I go ahead and plug my infinity in, this becomes a 0 plus 1. I get 1, so this converges. When both of the limits are infinite, then all we do is we approach the lower bound, or the lower limit. We say the limit as t approaches negative infinity from t to some number, any number you want. You can call this anything you want. The book calls it c, I think, but from t to b of the function, plus the limit as t approaches positive infinity from b to t. So you notice these two letters have to be the same. So if I choose a C or a B or whatever it is, they have to match, okay? And this is the general form. B is just a real number. Again, it can be any number that you want. If one or both of these integrals on the right here diverge, then the original will also diverge. Okay, so let's have a look at an example. So here it's improper because both bounds are infinite. So we're going to say the limit as t approaches negative infinity from t to 0 is the best number to use. All right, so use a 0 unless you can't, unless you know that, like if you plug a 0 in initially, you're going to get division by 0. Then you want to use another number, but otherwise use 0. Of the function plus the limit as t approaches positive infinity from 0 to t of the same function. Now, if you remember, this is the arctangent, right? The antiderivative of 1 over 1 plus x squared is the arctangent of x. So we're going to evaluate this, the limit of the arctangent of x evaluated from 0 to t, plus the limit as t approaches infinity of the arctangent of x from evaluated from 0 to t. And what happens is when I go ahead and plug in those bounds, we have the arctan of 0 minus the arctan of t. Well, in case you don't know off the top of your head, the arctangent of 0 is 0. So that's a 0. Okay. And over here, of course, we're going to have the same situation. Just notice they're swapped. Okay. The sign is applied to the other one. So what we have is we have negative arctan of t, the limit as t approaches negative infinity of the negative arctan of t plus the limit as t approaches positive infinity of the arctangent of t. And if I plug the infinity in, I have negative arctan of negative infinity plus the arctan of infinity. Well, remember, the arctangent has horizontal asymptotes at negative positive pi over 2. Okay, so we have these horizontal asymptotes at positive negative pi over 2. So this is going to be the negative of negative pi over 2 plus pi over 2, which is 2 pi over 2, or pi. If you want me to do a little review video on the derivatives and integrals of the trig, the inverse trig functions, let me know, and I'll do that. Okay, the third case that can happen is, so we had the first case, which either the upper or the lower limit or limit of integration was infinite. The second case is where both of them are infinite. And the third case is we have these unbounded integrands. So what you need to think here is vertical asymptotes. Okay. So the interval can be finite. Okay. But the function can have a point or points, more than one it could, depending on how big the interval is, of discontinuity or unboundedness somewhere inside or in between. It could happen at the endpoints too. But again, we're going to have these vertical asymptotic situations, and so we're going to have to redefine the integral in order to work with it. So here's the rules. There's 3 of them. If the function is unbounded at the left endpoint, or x equals to a, then what we're going to do is we're going to approach it and we're going to get really, 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 really close from the right-hand side. Okay, this is the left endpoint. So remember, left, right. So what we're going to do is we're going to come in from the right, real toward A. So we're approaching A from the right, and we're just, again, going to replace that weird number with a t, right? If we're unbounded at the right endpoint, then we're going to come in from the left. So we're going to approach that that right endpoint from the left. And, again, you can say this is the integral from, this is supposed to be a t, from a to t. You can call it a to b. You can call it whatever you want. And then the third case is where the interior is unbounded. So if I plug in A or B, that's not an issue. There's some point in between them for which if I plug it into my function, I'm going to have division by 0 or vertical asymptote. So the idea is that we're going to rewrite this integral. We're going to break it up into a sum from A to say C plus C to B. So again, those two points there, they have to, or those two values, they have to match. So let's look at an example. I know I did this one in class too. So we have the integral from 1 to 2 of x minus 2 to the negative 2/3. And if I think about that, x minus 2 to the negative 2/3 looks like this. So if you have to real quick rewrite it just to get a little perspective on it. And what I know is that if I plug a 1 in, I'm okay. But if I plug a 2 in, I have division by 0, right? So that's a problem. So my rightmost endpoint or my upper bound is an issue. So because that's the case, I'm going to say that this integral, so you write down the original, is equal to the limit as t approaches 2 from the left. Again, your interval goes like this. So you're coming toward that value from the left-hand side, and you're going to get really, really, really close to it, but not at it, okay? So I'm just rewriting the integral, okay? I go ahead and I integrate this thing, and I get x minus 2 to the 1/3 over 1/3, which is just 3 times the cube root of x minus 2. And I rewrote it in as a cube root because I know that many of you have difficulty if you were to plug this t in. You have difficulty like seeing what you're supposed to see. So if that happens, just rewrite it as a radical, and then you can see things more clearly. All right, so now I have to evaluate it from 1 to t. So it's 3 times the cube root of t minus 2 minus 3 times the cube root of negative 1. Remember, you can have a negative under an oddly indexed radical. So the cube root of negative 1 is just negative 1. And now you plug your 2 in. So I know we're getting really, really close from the left, but you actually just plug the 2 in. So we get 3 times 0 minus 3 times the cube root of negative 1, or negative 3 times negative 1. So you get a 3. And since you get a number, you say that this original integral converges. And what does it converge to? Converges to 3. Here's the same function, but my limits of integration are different. The left endpoint is fine, the right endpoint is fine, but there's something in between, right? Namely, x is equal to 2. So this is an interior point that's causing a problem here. So what I have to do is I have to break it up according to that third rule, which is here, okay? I have to break this up into the sum of two integrals. Now this is a shorthand notation. You still need the limit there, but that's legitimate notation. So anyway, what I have here is, the limit as t approaches 2 from the left, because again, you kind of think of it, 1 to 4, and think of your 2 in here. So you're coming in from the left to approach the 2 here, and from this endpoint, you're coming in from the right. So from 1 to t of my function, now we already found that in the example above, and that was 3, so I'm just making a note of that. Plus, the limit as t approaches 2 from the right, from t to 4. So you notice I'm going from 1 to t to 4. So those have to match. Those crisscross symbols have to match. And we have this. And of course, what we know, and I know this is messy, but I was trying to write it up really quick. What we know is we have 3 plus the limit, and this is just 3 times the cube root of x minus 2, because we did it above, but we're evaluating it from t to 4. And if I do that, so here it is a little more neatly, but with values plugged in. So if I do that and evaluate it, I have 3 plus that limit of 3 times the cube root of 4 minus 2. So I'm replacing this one with 4 minus 3 times the cube root of t minus 2. And this becomes 3 times the cube root of 2 plus, if I take the limit of this, the limit of a number is the number itself. But when I take the limit over here and I plug that 2 in, I get a 0. So this is going to go away. So what I'm left with is still a number, even though it's weird. So I can say that the integral from 1 to 4 of the quantity x minus 2 to the negative 2/3 dx converges, and it converges to 3 plus 3 root 2. The final thing I want to talk about is partial fractions. Sorry, background noise, so I had to shut the door. It annoys me. Okay, so partial fractions. And this is where you're going to be given a rational expression that you don't know how to integrate. No matter what you do, you can't integrate it. And so the idea is you're going to rewrite that rational expression as the sum of simpler rational expressions that you can integrate, okay? And then you're going to integrate. So here's a case where the degree of the numerator is less than the degree of the denominator. If the degree of the numerator is less than the degree of the denominator, it's pretty straightforward. If it's the other way around, where the degree of the numerator is bigger than or greater than the degree of the denominator, then you're going to have to use long division. So let's do a couple of these first, and then we'll do one that involves long division. Okay, so we have this function here, degree of numerator less than degree of denominator. So what I'm going to say is that this integrin is equal to 3x over the factored form of the denominator. And that means that I can take each factor in the denominator and I can write those as a sum of, we call it a, b, c, and so forth, all right? So a over x plus 2, so a over the first factor plus b over the second factor. If there was a third, you could do plus c over the third factor, and so forth. And then the idea is we want to multiply both sides by those factors. So when we do, if I multiply the left by the quantity x plus 2 times x minus 1, those cancel, and I'm left with 3x. And if I multiply each term here by the product of x plus 2 times x minus 1, the x plus 2's will cancel, and I'm left with a times x minus 1 plus b times x plus 2. And what you have to do at that point is you have to find a and b. So to do that, all you do is let x equal to the opposite of the factors that you have for each one. So here, if x is negative 2, I have a 0. If x is 1, I have a 0. So when x is 1, I get 3 times 1 is 3 is equal to, now if I plug a 1 in here, I get 0 times a, or 0, plus 3b. So I can solve for b, and I get b is equal to 1. So the idea is we want to solve and find those two values. And when x is negative 2, then I'm going to have 3 times negative 2 is negative 6 is equal to negative 2 minus 1 is negative 3 times a, plus negative 2 and 2 is 0, so the b goes away. And if I solve this thing for a, I get a is positive 2. So what I can say, what I want to rewrite, is that this integral here is equal to the integral of 2 over x plus 2 plus 1 over x plus 1 dx. And you can even do this if you want and put a dx, but you can separate them, right, at this point, if you want to. But I think at this point, you guys don't need to. So what we have here, so the antiderivative here is 2 times the natural log of x plus 2 plus the natural log of x minus 1 plus c. And I know on this exam, you don't have to simplify. They're not going to count that against you if you don't simplify. So this would be a perfect answer choice, and you could stop right there. But if you wanted to, you could use rules of exponents and bring that up, and that would be just as well. Here's another one. Okay, so degree of numerator less than degree of denominator. So we've got x squared minus x plus 4 over, if I pull out an x, I'm going to have x squared minus 3x plus 2. And that can be further rewritten as x times x minus 2 times x minus 1, right? So I'm going to have 3 factors here. And so I'm going to need another piece of paper. Let me just rewrite this back down. So we have x squared minus x plus 4 over x times, x cubed minus 3x squared plus 2x, right? Can be rewritten as x squared minus x plus 4 over x times x minus 2 times x minus 1, right? And so we're going to say that this is equal to a over x plus b over x minus 2 plus c over x minus 1, right? And at this point here, what we're going to do is we're going to multiply every term both sides. So I'm working here now. I'm going to multiply every term both sides by these factors here. When I multiply the left-hand side, I get x squared minus x plus 4 is equal to a times x minus 1 times x minus 2 plus b times x minus 1 plus c times x minus 2. Right? And at this point, I'm going to choose my x's, right? And the x's are going to be when x is equal to 0. So if I plug a 0 in for x, that becomes 0 and that becomes 0, and then I can solve for a. And x equals to 1, and then x equals to 2. So when x equals 0, on the left I'm going to have 4 is equal to, so I'm going to have a times negative 1 times negative 2, and b and c are going to go away. So what I have is 2a equals 4, so that means that a is equal to 2. Oh, sorry about that. When x is equal to positive 1, I'm going to have 1 minus 1 plus 4 is equal to, well, if I plug a 1 in here, a is going to go away. If I plug a 1 in here, b is going to go away. So what I'm left with is c times 1 times negative 1. So this means that I have negative c is equal to 4, so that implies that c is equal to negative 4. Is that right? Yeah. And if I plug in a 2, then what I'm going to have is 4 minus 2 plus 4 is equal to, now again, if I plug a 2 in here, a goes away. If I plug a 2 in here, c goes away. So now I can solve for b. So I have b times 2 minus 1. So this is going to give us what? 6 is equal to, this is 1 times to 2b. So this means that b is equal to 3. So what I have then is I have that the integral of x squared minus x plus 4 over x cubed plus 3x squared plus 2x dx is equal to the integral of 2 over x plus 3 over x minus 2 minus 4 over x minus 1 dx. And if I integrate each one of these, then what I'm going to have is, this is all natural logs, right? And these are constant multiples in the numerator. So, you can think of this as 2 times the integral of 1 over x plus 3 times the integral of 1 over x minus 2 minus 4 times the integral, like this. That's how you can think of that, okay? So what I have is I have 2 ln absolute value of x plus 3 ln absolute value of x minus 2 minus 4 ln absolute value of x minus 1 plus c. And again, if you wanted to, you could bring these up as powers, and then you could use the rules of for addition and subtraction of logarithms, but again, you don't have to, so why go there? Why go there? All right, now let's look at one where the degree of the numerator is bigger than the degree of its denominator, and that's just called an improper rational function. Okay, and you're going to use long division on these. Oops, there we go. And your goal is to express the function as the sum of a polynomial and a proper rational function. So here's a simple example. degree of numerator bigger than degree of denominator. So I'm supposed to use long division. Now look, if you don't like the way I wrote this, you can write it. You can swap those around if you want to, and you can write it like this. All right, and divide in. So remember we say x squared goes into x cubed x times, and then we multiply this back through. So we say x times x squared is x cubed, change the sign. X times 1 is x, change the sign. And don't forget to write your missing terms as 0x to the whatever, have to go in descending order, right? So, you know, what we get is a 0, a 0. We end up with a negative x, another 0. So this is our remainder. And how we write these is we take this x minus remainder over divisor. Right? So this is what I'm dealing with now. And this is nice because what I can do is I can rewrite those as their own little integrals like I did here. Now, the antiderivative of x is just x squared over 2. Easy peasy. This one I got to use a little bit of u substitution, so I went ahead and did it just to remind you. So I'm going to replace this with a u integral, which would be negative 1/2, bringing that 1/2 out front, 1 over u du, which is just the natural log of absolute value of u. And if I back substitute, I get this in here. So I'm assuming that you guys are sophisticated enough with this stuff that this is not a problem for you. Okay, and that's it. So I'll be more than happy to go over any problems or questions that you have with these. I know this was fast, but I already taught it. I know it's been a while, but you know, it's your job to keep up with that. So if there's anything that I did in the video that's confusing or you want a few more examples, please don't hesitate to ask. Remember to message me on Etsy and go ahead and try the homework that's on WebAssign. It's due on Thursday. And let me know if you have any questions, all right? Have a good rest of your day. And now I'm going to try and shut this thing off.